Hello and happy December, dear chemistry enthusiasts. It looks like we were back in COVID times where all of our learning was virtual and through the computer. However, not because it is virtual, it means that it must be boring or difficult to understand. Today, with my peers,
María José Armenta.
And Sofía Muñiz.
we will be learning about carboxylic acids and esters, which was considered to be the hardest topic of organic chemistry. But we're going to teach it in a way that it is concise, easy, and fun to remember. So let's get started. This is a little bit about the overview that we will be covering today. And now, the introduction to organic chemistry. Organic chemistry, in simple terms to remember, it is the study of carbon-containing atoms and compounds. So it studies the structure, the preparation, the composition, the reactions of this carbon-containing compounds. Now, I like to remember carbon as the component of life, and it has the ability to form covalent bonds with many elements to create a various infinite number of structures. If we look at the image in a covalent bond, it completes the last shell. If we count the atoms, it has 8, meaning that it is complete. But why organic chemistry? The purpose. So basically, they studies the chemical reactions including inside living organisms. We humans are living organisms. And it plays a fundamental role, for example, in molecular medicine, pharmaceutics. It can also help predict what is going to happen when two elements combine. And remember, carbon is the molecule of life. Now let's begin. Carboxylic acids. They are a homologous series with the prefix homo that helps us remember that they have the same functional group, the COOH. What does this mean? It has a double connection with the oxygen atom and a single bond with the hydroxyl group. If we take a look at this image, it has the double bond and the single bond. And we will take a look at the naming with our friend Maria Jose later on. About the characteristics, carboxylics are polar substances because the electrical charge is not balanced. It is partial positive and partial negative, and it is present in our daily lives in a wide variety of uses. More of the characteristics and properties. We'll talk about solubility. Solubility is, as the name says, the ability to be soluble, for the solvent to dissolve in the solution. Now, usually organic compounds are hydrophobic. Prefix hydro, water, phobic, it repels, and they are insoluble in water. However, carboxylic acids, because they have a non-polar part, which is the hydrocarbon chain, and the polar part, that is the carboxyl group, they can be dissolved. Now, what is the rule or the proportion? The higher the molecular weight, it becomes insoluble in water. So if it has like approximately 5 carbons, 4 carbons, 2 carbons, or 1 carbon, it becomes easy to dissolve in water. So how does the proportion go? As the number of carbons increase in the acid, the solubility decreases. If we were in an exam with our professor, Mr. Kevin, and we get the following question: which of the following carboxylic acids has the highest solubility in water? Take a minute to think and answer. And the answer is methanoic acid. This is because it contains only one carbon, and the least amount of carbons it becomes more easily to dissolve. I mean, we can see here in the presentation, it says methanoic acid will be very soluble in water and it's ready to engage with other hydrogen bonding. One more about the characteristics. Carboxylic acid have strong intermolecular forces. If it has a strong intermolecular force, it's going to have a higher boiling point and a higher melting point because it requires more energy to break those strong bonds. The boiling point is higher than the ones in alcohols, ketones, ethers, and even water. And it also has a high melting point. The melting point has a lot to do with the fact of it being a saturated or an unsaturated. Saturated carboxylic acids have single bonds between the carbon atoms, and unsaturated have single, double, or triple bonds between the carbon atoms. They're also considered to be weak acids, different from other hydrochloric acids, which are more stronger. And very importantly, carboxylic acids are partially ionized in a solution, so they don't give up entirely their hydrogens. And they're also proton donors, according to our Bronsted-Lowry theory and concept. Now, let's take a look at this small question. We see that the first one is a saturated acid because the bonds between the carbons are single. And the one below, it is an unsaturated acid, linoleic acid, because it has also double bonds between the carbons. And it has the carboxyl group at the left. Other properties, let's know that if we react a carboxylic acid with a metal carbonate, we produce salt, water, and carbon dioxide. An example is the ethanoic acid. When it reacts with potassium carbonate, we produce a salt, a water, and carbon dioxide. And how are this made? We're going to deeper into how they're made, but very briefly, if we take an alcohol, it can be butanol, and then we take an oxidizing agent, we produce a carboxylic acid.
Now, of course, this is a very difficult and complex topic. However, properly understanding and internalizing the structure and IUPAC nomenclature promise to facilitate this process. Now, we will begin to understand the structure of carboxylic acids. Carboxylic acids are an organic compound that contains the carboxyl functional group and additionally a hydrocarbon group radical. Now, this must seem abstract, but we can understand it by its components. First, we have a carbonyl. A carbonyl is a carbon that is double covalent bonded to an oxygen. And we also have a hydroxyl group, that is an oxygen that is single bonded to a hydrogen. Now, when these two come together by the means of the carbon that they share, we have a carboxyl, and that is the carboxyl group that we are referring to in the definition. Now, this carboxyl is not alone. By the way, it has the formula of COOH, which will become familiar in the future. Now, we don't only have the carboxyl, we have a hydrocarbon, and a hydrocarbon is a familiar concept, even though you don't know it yet, because it is an alkane. Now, when we have all these together, we have the general formula of a carboxylic acids, that is RCOOH, when R is a radical that can be any of the hydrocarbon existing. Now, we can understand it, as our friend Sophia said, as carbon being the main component of life and organic chemistry as a whole. Here we have illustrated the general formula, where C, or carbon, is the center of it all. Carbon is double bonded to oxygen to become a carbonyl group. Now, this very same carbon is bonded with an oxygen, and this oxygen, the second oxygen, is bonded with a hydrogen. And now, going back to our carbon, is bonded to the radical that can be any hydrocarbon. Now that we have understood this, we can pass to understand how we give them a nomenclature. Sophia, please pass the slides. Yes. Now, even as this is a very complex compound, chemists must be able to understand each other and preserve and build knowledge around them by having a standard way to name them. So the IUPAC organization formed these guidelines so that we can all around the world name them equally. First, you must select the longest aliphatic. By the way, by aliphatic, we refer to a linear compound, a compound that is not in a ring structure. Select the longest aliphatic carbon chain containing the carboxyl group. By the way, this carboxyl group is kind of like the general formula, is the part that doesn't change. And then you change the E ending of the parent alkane. The alkane is the hydrocarbon name, and is replaced by the suffix oic acid. So at first we can analyze that all carboxylic acids end with acid. So that's the first way in which you can, by first sight, recognize them. The parent alkane is very important because it is kind of like the differentiator between multiple carboxylic acids, as is the variable part, is the radical, is the part that makes them different. And so that you don't get confused, the alkane is the same as the hydrocarbon referred. Then, as an exception, when the aliphatic chain contains more than one carboxyl group that can be easily recognized as having more than one carbon atom, as the carbon atom is kind of like the center of the carboxylic group, the total number of carbon is counted, and that being the number of carboxyl groups is represented by Greek numeral prefixes that are also very familiar to us if we've read at least once a chemistry book, that is di, tri, tetra, penta, hexa, and so on. This only when there are more than one carbon atom in this compound. Then this carboxylic acid is named by adding these prefixes, if there are any, and the suffixes to the parent alkyl chain. Then Arabic numerals are used for indicating the position of the carboxyl group in the compound, if it's necessary. However, it is important to clarify that aromatic carboxylic acids, so the ones that are in a ring structure, are named after the very same parent compound. So we can further illustrate this. Here are some examples. One of the most important and easy to recognize carboxylic acid is methanoic acid, where the radical is an H and is forming one of the most elemental forms of a carboxylic acid. And there are other where the third rule is employed, where we locate the position of the carboxyl group and so on. Now we may proceed to the topic of esters. An ester is very similar to an acidic to a carboxylic acid. And that is why we must first understand carboxylic acid before we pass on to esters. An ester is an organic compound derived from a carboxylic acid, in which one of the hydroxyl group, remember the hydroxyl group that was a key part of the carboxylic acid, is replaced by an alkoxy group. Now, we must understand what an alkoxy group is. An alkoxy group is an alkyl bonded, single bonded, with an oxygen. An alkyl is kind of like a hydrocarbon or an alkene, however you want to call it, that is missing one H it usually should have. So now that we understand what an alkoxy group, we are going to learn the general formula through our previous knowledge of the carboxylic acid general formula. First, we have the carbonyl, which we already know, and then where we should be having a hydroxyl group, we now have our alkoxy group. And then our radical can be an alkyl, an aryl that is the same as an alkyl except for our ring structure hydrocarbon, or a hydrogen. As you can see and may be confused, there are two radicals or two R's, but they are not the same. One is a simple radical and one is a radical prime. The simple radical can be an alkyl, an aryl, or an oxygen, as I said. However, the radical that is part of the hydroxy group, of the alkoxy group, can be an alkyl, an aryl, but it cannot be a hydrogen because otherwise it would form the general formula of RCOOH, which, as you may know, is a carboxylic acid. And an ester is not a carboxylic acid, it's a variation of it. So it cannot be oxygen. It can be an alkyl or an aryl, but never an oxygen. Now, as carboxylic acids, we must also give it a nomenclature so that we all chemists can understand each other all around the world. These rules are rather simple. The group name of the alkyl or the aryl group portion is given first and is followed by the name of the acidic portion. The group name of the alkyl or aryl group is unchanged. It stays the same, and if we study alkyls or aryls, we know that they have the same termination, that is the YL. Then the IC ending of the parent acid, that is a carboxylic acid, of course, is replaced by the suffix ate. Then we apply to the acidic portion official prefixes, as we have established before, to indicate the number of carbon atoms on the main carbon chain. Here are some of the most common examples. What was methanoic acid? Now here is methyl methanoate acid if it was an ester.
Okay, thank you, Maria Jose. And I think we have the topic a little bit more clear now. Let's dive into the formation reactions or the synthesis of carboxylic acids. This could personally be one of the hardest parts to remember, but let's take a look about one of the ways to form carboxylic acids, and it is called ozonolysis. So ozono means that they use ozone, and lysis, basically the suffix, they break down, or it's like a reaction. So this type of organic chemical reaction, the two examples that I will show that are under reducing conditions that lead to aldehydes, and then under oxidizing conditions, it produces a carboxylic acid and a ketone, as we see in the image. And now for this drawing, we used hydrogen peroxide to form carboxylic acid, but we could also use KMNO4. That would also work. It depends on the type of reaction that we are studying. So basically on the ozonolysis synthesis, it refers that in the organic chemical reaction with the help with the ozone, they can produce alcohols, aldehydes, ketones, and the carboxylic acid itself. But in order for the carboxylic acid to be produced, it needs to be under oxidizing conditions. On our left, we have the drawing of the reducing conditions. On our right, we finally have the example of the oxidizing conditions. However, also chemistry on an A level Cambridge explains that we can also get carboxylic acids from the oxidation of primary alcohols. Alcohols can be classified into primary, secondary, and tertiary. And the characteristic of the primary alcohols is that the functional is bonded to a carbon atom that is bonded to one other carbon atom, which is exactly what we can see in ethanol and propanol. Methanol doesn't follow this rule, but it is still considered a primary alcohol, and it works as well. Now, in order to produce the carboxylic acid, we're going to have a reaction to produce the aldehyde. Now, two molecules of oxidizing agent to oxidize a primary alcohol and later produce a carboxylic acid, as we can see on our image. However, once the aldehyde is produced, it needs to be heated in order to finally produce the carboxylic acid. And to make a quick sum up, it requires two molecules for the oxidizing agent, and all the excess also needs to be part of the reaction, and it must be heated. The fact is that the carboxylic acid are the most oxidized functional groups of carbon. And we can reverse the process in two different ways. First, we can take a reducing agent like lithium aluminum to give back to our alcohol the proton that we took, but also we could use decarboxylation, as the word says explicitly. It's gonna decarbox, like it's gonna take the carbon back using heat. So it's gonna replace the carboxylic acid with a hydrogen atom. However, meanwhile, in our research, we also learned that we don't always want to get rid entirely of the functional group of the carboxylic acid, and there's a process called the Fischer esterification, which is a reaction in which we can turn the bad smell of the carboxylic acid and turn it into a pleasant smelling and popular ester.
Thank you, Sophia, for that amazing explanation. Now, I am going to delve into the formation reactions or synthesis of esters. So to understand this concept, basically, we need to know that esters are born through a process named esterification, which is a reaction where a carboxylic acid partners with an alcohol, creating as a products esters and, of course, water. This is actually described by the equation that we can see in the slide presentation. However, esterification doesn't end here. It has another important component, which is the acid catalyst. This is a really important concept since, to make an analogy, is like the matchmaker of the process. For instance, the catalyst is the one that enhances the carboxylic acid. It gives it more reactivity, and this, of course, causes the reaction to be more efficient and to be smoother. An example of an ester synthesis can be the reaction between ethanoic acid, which is a carboxylic acid, and ethanol, which is an alcohol. This creates ethyl acetate, that for those who are unfamiliar with ethyl acetate this is basically a fruity smelling ester that is commonly used in perfumes and as a solvent. Now, already having dived in the synthesis, we are going to get into the organic hierarchy. So basically, before telling the organic hierarchy of carboxylic acids and esters, I am going to give a brief context on what organic hierarchy actually is. Can you pass this slide, please? So basically, organic hierarchy in chemistry is a system that helps us organize different compounds based on their structure, functional groups, and chemical properties, like, for example, reactivity. This system covers everything from simple compounds to more complicated structures. And now, knowing this, we can take a look in the order of the carboxylic acids in the table of organic hierarchy. So as we can see in the image, carboxylic acids are right at the top. This means that they have unique properties, and this makes them the highest priority among the carbon-containing functional groups. And they, of course, due to this, have a crucial role in several chemical reactions. Just below carboxylic acids, we can find esters. Esters are closely related in properties. This actually gives them their position. For instance, in comparison to carboxylic acids, esters have a similar structure, and also we can see more commonalities due to the fact that they are a direct product of carboxylic acids and alcohols. Now, we are approaching the end of this presentation, and we are going to delve in the uses and examples of both carboxylic acids and esters. But before delving in these uses, it is important to understand that, as I have already mentioned, both carboxylic acids and esters have similar properties. This makes them have similar uses as well, and even some of the uses are the same. However, to avoid being repetitive, I am going to give different uses for each. So first, let's start with carboxylic acids. So carboxylic acids are used in everyday things, like, for example, in food production. They help enhance the flavor of some products, like, for example, acetic acid is used in vinegar, and they also help preserve the food. Another of its important uses is in the pharmaceutical world. For example, they serve as an important factor of various drugs. In aspirin, they are used, and as we know, aspirin is really important as it is a common pain and inflammation reducer. The textile industry also benefits from the use of carboxylic acids. They are used in the dyeing process of different materials, like for example, while painting clothes. Likewise, some carboxylic acids, like citric acids, are found in household cleaners, for example, for stain removals or any other dirty things. At last, we can see them in skin products, like more specifically in exfoliating products due to their properties. Now, having already go through the uses of carboxylic acids, we can go into the uses of esters. So at first, esters are utilized in the production of inks, for printing, of course, contributing to the ink's viscosity and the drying properties. Additionally, we can find esters in pleasant scents, like in perfumes and other personal care products. These I already mentioned while talking about the synthesis, that the ethyl acetate is an example of an ester that can be used for a specific aromas. Another example is that esters that are derived from animal fats or vegetable oils are used in the production of fuels, but not just any fuel, environmental friendly fuels. And finally, some esters are used as solvents in paints, coatings, and varnishes due to their ability to dissolve various substances. Now, these are all the uses. Of course, we can find more out there, but these ones are the main. So, we have reached the end of this presentation. I hope that my chemistry friends, you have learned a lot about carboxylic acids and esters.